So how do we tell the difference between gravity waves generated from, let's say, two neutron stars colliding, as opposed to two black holes, or maybe a black hole that's like a singular black hole that's making some kind of noise on its own?
That poor little thing's hard to detect. He's quiet. So there's a reason why the LIGO scientific collaboration and our counterparts in Europe and Japan are so big. It takes a lot of people. So there are a lot of people that have to do it just to understand that it wasn't an earthquake, that it wasn't, like, there's so many noise sources that cause things to jiggle. So that's an amazing thing that happens. The people who understand the quantum shot noise of each photon hitting a mirror, like, you can go down there's so much stuff that happens. From my point of view, the reason why you have people like me working with detectors is not because they need my help on the detector, right? They do not want me anywhere near it. It's because we can theoretically predict what Einstein says is the equations say is the difference. So what happens is that astrophysically speaking, black holes are bigger. Neutron stars have a mass limit. We're fuzzy on exactly where that limit is, but we certainly can tell the difference between, I can tell you if we see the full signal, which means I see an in-spiral, merger, and a ring down, and I see that full signal, we only can see that with current detectors when they're pretty massive. They're always binary black holes when we see that full signal, because black holes can be bigger. Mm-hmm. Neutron star binaries they're smaller masses, so their signal is weaker. And so we see them orbit each other for a long time, but we don't see them merge. Mm. So in a lot of ways, it's hard to distinguish neutron stars and black holes because in that in-spiral part, they look very similar. Mm-hmm. There are subtle differences because the neutron stars feel each other, so they get tidal effects that black holes don't really. Mm-hmm. But it is really hard. So we distinguish a lot based on the mass that we predict by comparing it to the theoretical predictions that people like me produce. Mm-hmm. So we use our understanding of the theory to figure out what all the physical parameters are. And then we use our understanding of astrophysics to say, those are the parameters of a neutron star versus a black hole. Okay. And then we start to deeply search for these other effects that could only be from neutron stars, like tides. But they're just a little bit harder in the data to see. But that's very exciting. And then we don't really know the equations of the matter inside neutron stars. So that impacts all this. So one of the big things we would like is to get enough frequency band to see the merger of the two neutron stars, because that would reveal what actually was the state of the matter inside the neutron star.
Yeah.
That would be cool.
That would be really cool.
Mm-hmm. That'd be one of the coolest things. But we're not there yet because our frequency cuts off before.
When you say state of the matter, do you mean kind of like solid, liquid, gas, plasma, or do you mean the actual density in elements?
The density, the pressure.
Okay.
Because there's no lab on Earth where you could reproduce what's in the neutron star, so it's a big unknown. Like the first binary neutron star merger was fun because people are like, it made platinum, it made gold. Like, we realized it could make all these elements, in part because we saw the electromagnetic counterpart to two neutron stars merging, which means telescopes that look for light also saw the same event we saw with the gravitational wave detector. So we learned a lot about it because we had all these ways of studying it. Mm-hmm. But it would be really great to so those neutron stars, when they merge, they disrupt all that incredibly dense material, and so we could learn a lot about it just from the gravitational waves by how it merges, because we can simulate a bunch of different choices for the matter, and so we would be able to some extent know, it's this kind of thing inside there.
Mm-hmm. Okay, that does remind me a lot of my field, which is geophysics, mm-hmm. right? And what especially reminded me is when you talk about noise. So for polar geophysics, the even more niche thing that I research, you'll fly a plane over an ice sheet, and then you'll have a gravity meter on the plane, and to even so to calculate for your position in space, you have to have a supercomputer on the plane that corrects for all of that while you're flying this gravity meter. And then the actual deciphering what is a measurement and what is noise is the single greatest challenge in using that kind of data. So I would imagine for even more precise gravity meters like LIGO.
We need 10 to the minus 21.
Yeah, which that is absolutely insane. Yeah.
It's crazy. Yeah, but it's fascinating, isn't it? Like what we can actually do if you have enough people working on it. It's like, wow, that's amazing that we can do that.
Yeah.
Pretty cool to be able to fly over detecting things too.
And then, so you talk about how neutron stars differ in their kind of, I forget what this.
The orbit.
Orbital.
The tidal disruption.
The tidal disruption, like the different phases. There's the merging and the ring down, and then.
Everybody does that.
Okay.
They have inspa, what we call inspa merger ring down. All it means is I were two objects, I became one mushy object, now I'm a single object. That's what it means. Yeah. They all, both binary black holes and two neutron stars go through that same process, but LIGO's, the frequency that neutron stars merge is a little too high, and LIGO's not sensitive to it.
Okay.
Just because we know there is fundamental noise like shot noise, so we have to build a new detector to try to get at that frequency.
So what about black holes that have a lot of material around them? Do they experience, like are you able to pick up some kind of like tidal frequency from black holes that are...
Not on the gravitational waves.
Okay.
Because you need a lot of mass to perturb a gravitation, That's a lot. It's very hard to, like you can imagine, forget the black holes LIGO sees right now, because they're actually not that much. They're like a little bit bigger than a neutron star, up to about 200 times the mass of our sun. But those are relatively small black holes when you have, black holes at the center of the galaxy, which are 1 million to 1 billion times the mass of the sun. So they're the ones at the center of our galaxy we would expect to be surrounded by matter if it's an active galaxy. And you can even imagine a binary black hole pair sitting there in that accretion disk. People look for those signals. It is more likely that you would see that from an electromagnetic disturbance than it would be from a gravitational wave. So when we look for electromagnetic counterparts, we call them, it's because something's happened, either binary neutron star where you expect there to be an electromagnetic counterpart if it's close enough to us, because there's a limit of what we can see, or black holes in some kind of rich, dense environment, then we would look for the light that's being disturbed because of the stuff. We have not seen that from black holes. It'd be cool. We expect with the space-based mission, LISA, which will fly somewhere around 2035-ish, we expect to be able to see electromagnetic counterparts to the big boy black holes, the million solar mass black holes merging.
So say that I take, Andromeda, the Andromeda galaxy is getting closer to us as time goes by. So I fast forward. I'm not sure the exact time scale before our galaxies merge.
I don't know either. Anyway.
Some
very far away.
Point
Our sun's
in the very
already
far
probably
away.
red gianted. Yeah.
Yeah. Some point in the very far away future, we're all disintegrated from the sun's following our planet up. Does the supermassive black hole at the center of Andromeda merge with our black hole?
So this is one of the big questions in astrophysics. And so that's why one of the reasons why people are excited about detectors like the space-based, because it would actually be able to measure those two black holes merging, and it will solve this question of whether or not when these galaxies collide, there's a lot of reasons to think that those black holes do find each other and do merge, but it's not definitive. So we need that evidence, and the gravitational wave would be definitive because we would know the masses, we would know that they did. So that's one of the big excitements about the space-based mission.
Yeah.
And we'd also see the single black holes that are big. I sang Beyonce in my head, the single ladies, for a second. Good thing I didn't do it out loud. So they would also, Lisa also can see like a small thing fall into a really massive black hole. So we could look for those. We can't see that with ground-based detectors. Yeah. So there's new fun things.
So how does, so if I have a black hole that's a lot larger than another, that larger one is going to swallow up the smaller one?
It could.
It could?
I mean, it doesn't, you can't disrupt a black hole. So the end state is always another black hole.
Okay.
Not quite the same mass as adding the two together, but close because we lost some mass to radiation. We converted some energy into radiation.
Yeah, there you go.
Same thing as the angular momentum.
Yeah, that's
Yeah.
Yeah.
So what's crazy about these mergers of these black holes is that the percent of energy that gets converted to gravitational waves is like 5%, which is huge energetically. Like it's more than the light we see shining. It's just that we were completely blind to it. So they're incredible producers. It's just that gravitational waves are hard to find. So.